So this video is going to be a quick summary of all of our different types of triangle centers. So the first one I'm going to talk about is the Medicenter or Centroid. Remember, that's the center of mass of a triangle. So it's always going to be inside the triangle because that is the balance point of the triangle. And we find that by finding the intersections of our medians. And medians are just the bisectors of the sides. So if I take a side and I measure it and I find the midpoint, let's say it's that, and then I connect that midpoint to a vertice, that is a median. So that line right there is the median. I can find other medians by taking another side here and finding the midpoint, which to me looks like there, and then connecting that vertex to that median. Again, we're not worried about the angle here. It is not necessarily 90, even though it sort of looks close to it. The key is that it cuts this side in half. That's what a median is. It connects the vertex to the midpoint of the opposite side. So then using blue, I can go to this side and say, well, the midpoint looks to be about there. And if I connect that midpoint to my opposite vertex, I should hit there. And it cuts this in half because it's a median, that line right there. And the intersection of the three medians right here produces our centroid or Medicenter. And again, Medicenter comes from median, so it might help you to remember Medicenter over centroid, but both are the same thing. And again, this will always be in the middle because it is the balance point of the triangle. So if I draw another triangle, this time I'm going to talk about the Incenter. And the Incenter has to do with the angle bisectors and where they intersect. Whoops, it's an N. Angle bisector intersection. So if I draw a triangle, let's do one like this. So the angle bisectors are the lines that cut the angles in half. So if I do a line here, that looks about half to me. I've got half and half. If I draw a line here, that looks about half to me. And I draw another line, maybe here. It looks like it cut it in half. The intersection of those angle bisectors will be our incenter. Remember, the incenter comes from the idea of that there's a center to a circle that sits in the middle of our triangle. I won't draw it because it'll make it look awful, but there's a circle inside here centered on the incenter that touches each side only in one spot. So it is tangent to each of those sides. And that's going to be our incenter right there in the middle. It is the intersection of the angle bisectors. So we've had side bisectors, also known as medians, right? And their intersection, that produces the Medicenter or the centroid. We've had angle bisectors, which are going to produce the incenter. Both of these are always going to be inside the triangle. We have a balance point here, and then we have an incenter, which is the circle inside the triangle. So now we're going to start breaking outside of the triangle. I'm going to talk about the Orthocenter. So the Orthocenter is not always inside the triangle. But the idea of the Orthocenter is it's at the intersection of your altitudes. Or we could call them orthogonals. Or we could call them perpendiculars, because they're all the same thing. So where they intersect is going to be where the orthocenter is. Now, it might be helpful to think of the altitude, because I always forget these start from the vertex and drop down to make a 90-degree angle with the opposite side, making them different than another one we're going to talk about later. And that's what altitudes are. It's the height of the triangle. But orthogonal and perpendicular give you a hint that it has to be a 90-degree angle. So I will draw something like this. There's our triangle. There's our vertices. The key, again, is to think of it as altitude or perpendicular or orthogonal. What are you going to think? And that the idea is we start from vertice and we drop to the opposite side and we hit that at a 90-degree angle. So when I draw this, there's lots of lines I could draw from that vertex. I want to make sure it hits it at 90 degrees. So because this side looks to be acute, if I draw a line from there to there, I get an acute angle. If I keep going and keep going and keep going, eventually I'll get to a point where there's a 90-degree angle. And to me, it looks about right there, 90 degrees. You can check that with a protractor, but that seems to be the 90-degree line right there. If I move it over a little bit, it doesn't hit that point. So that was pretty good. I can do that for the other sides as well. Again, the key is not to show that these two, that this is not a perpendicular bisector, so it does not bisect the opposite side. As you can see, this is really small and that's really big. But it does drop down from a vertex at a 90-degree angle to the opposite side. So if I pick another vertex, like this one right here, I can drop down at a 90-degree angle, and I'll not guess on this one. Looks like there. So if I drop down from a 90-degree angle from our vertex, I'll produce another altitude or height of the triangle. So the height of the triangle this way is that guy. And then I can also go to this last side here and do the same idea. So I'm going to do that in blue this time. So finding the point here, looks like, where if I draw a line from there to there, it'll hit this at a 90-degree angle. And for this triangle, the orthocenter happened to be inside the triangle. So it's at the intersection of all of our orthogonals, or our altitudes. So the lines that drop from the vertex and hit the opposite side at 90 degrees, their intersection was here inside the triangle. If I had an obtuse triangle, I would have a little bit harder time. You can see from the last page examples, we have an acute triangle with it in the inside. Obtuse, you have to actually extend the sides out for them to hit it at 90 degree. There's no line that you could draw inside the triangle from this angle here to have it hit this side at 90. So we had to extend it out to where it would hit 90. Same thing here. This side right here isn't long enough to intersect at 90. So you have to extend this out and have it hit at 90 there, and the intersection is actually outside the triangle. That's the orthocenter. For right triangles there, if they are, if you do the altitudes here, the height here from this side, the height here from the red side, they will always intersect here because that'll be their 90-degree angle drop, and then your last orthogonal here will always intersect at this point, the point that's next to the 90-degree angle. So that's the orthocenter. It's the intersection of the altitudes of the triangle. Remember, altitudes are the line from the vertex down to the opposite side at 90 degrees. So we have medians, which cut the triangle in half, right? The side length in half. We have the incenters, the bisectors, that cut the angles in half, the angle bisectors. And then we have the orthocenter that drops from the vertex and hits at 90 degrees. When we put some of these together, we get the circumcenter, which is our last center of the triangle, the circumcenter. Remember, the circumcenter is a center of a circle that hits all the vertices of your triangle. So the circumcenter can be sometimes in or outside the triangle, and it's going to be at the intersection of your perpendicular bisectors. So it's kind of like the median of a triangle, wherever I put it. The median of a triangle. The medians cut this in half, right? So it bisects this line, and that's what circumcenters are going to do. They're going to be bisectors, but they also care about the angle that it leaves at. So it's when these two are both the same, and there's a right 90-degree angle there, that we have a perpendicular bisector. So if I draw a triangle, let's draw an obtuse one, just for fun. There's my vertices. I'll color those in for those of you that get bothered by that. So those are our vertices. If we were to take a side and find its halfway point, there's its midpoint right there, and then draw a line that goes off at a 90-degree angle from there, looking like that, and I'll extend that out. Notice it doesn't intersect with the vertices. That's the big difference between that and the Medicenter. The Medicenters always go from the midpoint to the vertice. Circumcenter often does not. It's just a line that leaves here at 90 degrees that goes through the midpoint of the side. If we find the midpoint here, looks to be, I don't know, that looks like the midpoint. Let's mark these as midpoints. So those are midpoints. And we draw a line that hits, leaves here at 90 degrees. If I draw a line here, that's going to be an acute angle. So I want to start pulling it out a little bit more, and then about right there looks to be 90 degrees for me. Then I can do the same thing for my last line. I'll do that in blue. Here's my line segment. The middle of that looks to be, I don't know, about here-ish. So there's our midpoint there. It's probably not perfect. But then I take that and I draw 90 degrees. So if I take that midpoint there and I draw a 90-degree angle, it looks to be about here-ish, right there. I drew a pretty bad line. Where those intersect is going to be our circumcenter. So that's the center right here, C, of the circle that hits every single one of these points. And by every single one of those points, I mean every single one of those vertices of the triangle. So the intersection of the perpendicular bisectors is the circumcenter. Perpendicular bisectors are bisectors, so they cut the sides in half, and they're perpendicular, so they leave at a 90-degree angle. And they do not always and often, rarely intersect with the vertices. That's the big difference between that and the Medicenter. So we have bisectors of each side, and they leave at a 90-degree angle. Where they intersect is the circumcenter, which means that since this point right here is the center of a circle that hits every single vertex, it means that from here to here, from here to here, and from here to here are all equal distance. So I'll do 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, because they are radii of the circle. So the circle that goes from here to here, I'm going to draw a terrible circle, has a center there, which means that those are radii. So not only do we have perpendicular bisectors that form the circumcenter, but we also have equidistant points. This vertex is equidistant to the center as this vertex is from the center. So all of these are going to be equal because we have a big outside circle centered on this point at the circumcenter. So those are our 4 different types of triangles. Again, to review them real quick, we have the Medicenter, which is at the intersection of the medians, so the intersection of the lines that cut the sides in two. The Incenter is at the intersection of the angle bisectors, so where the lines that cut the angles in two, and both of those are going to be inside the triangle at all times. Incenter is going to make a circle. I'll draw it now. Centered about the incenter, and notice that circle is hitting the triangle, and it is tangent to these points, so it means where it hits the sides of the triangle, it'll be at a 90-degree angle, which may or may not be on those lines that I drew, the angle bisectors. It often looks like it though. The orthocenter is at the intersection of the altitudes, so if you take a vertex and drop a line down at 90 degrees, it'll intersect the side at 90 degrees, and all of those intersect to be the orthocenter. And then last but not least is our circumcenter, probably the most complicated one. It's the intersection of the perpendicular bisectors, so it's a triangle with bisectors. The sides are cut into 2 equal pieces, and from there they go off at a 90-degree angle and intersect. For obtuse triangles, they go outside the triangle. For acute, the circumcenter is inside, and for a right triangle, it's somewhere on one of the sides of the triangle, often on one of the legs, I believe. So those are our 4 different kinds. Hopefully that worked as a nice little review. See ya next time.